is going to talk about associative algebras and the representation theory of gradient restricting vertex algebras.
Okay, so should I start?
Yep,
okay.
Whenever you're ready.
Okay, so first of all, let me make sure that you can see my slides because I'm actually the lecture user.
See them? Yep, they look great.
Okay, so what I want to talk about is a recent work of mine. Basically, I did this in the summer. So actually, I wanted to actually see that the main goal is that for all these kind of research is the following. So before I just go to the technical thing, is that I myself do want to develop the whole theory of vertex algebra as a general theory, not just a framework for some examples. So I think that given if you have some algebra, you want to develop the representation theory, basically there are two things you need to do. Probably for vertex algebra there are more, but see, at least there are two things. One is that we have achieved a lot is the tensor category. So basically representation theory to a certain extent is that we want to construct these tensor category, prove all the properties of a tensor category. So for this part, we have achieved a lot. So Jim Lepofsky and I started in 90s, and then later we actually developed the whole theory. So now we actually have not just like a braided tensor category, but we actually constructed so-called a vertex tensor category, which is much stronger. On the other hand, see our construction assume a lot of conditions, so you need to first verify these conditions. And when you verify these conditions, you need to use a lot of properties of the vertex algebra and the modules. And usually in algebra, one of the main sort of a tool or method or framework is those things like the homological algebraic tools. So you need to develop this cohomology theory and so on. So I did introduce the cohomology and so on. But see, these things actually it's far from really developed. It's just we have this cohomology, and I think I actually proved jointly with my former student that the first cohomology, for example, related to the computer disability and so on, but still there are conditions you need to verify, which are not easy. So I think that because these vertex algebra are actually analogs to commutative and associative algebra. So we should actually, my hope is that in the future we have to develop a theory of vertex algebra, which actually in some way always we can say this part is analogs to associative algebra, what part of the associative algebra, and the other part are also analogs to associative algebra part in what sense. So the one of the things that the cohomology theory is not well developed, so we even do not understand some of these things, what's going on. So one of the things that we can look into associative algebra. If we have a powerful associative algebra, probably we can actually get some hint, and then we can develop that. So this is one of the reasons I wanted to find some nice associative algebra. Okay, so now I start the technical things. Okay, so what I will basically talk about is, first of all, I do find the correct associative algebra, so that is actually nice. And then I will discuss sub-algebras of this associative algebra, including the familiar Drew algebra and also those generalization by Donnelly Mason. And then I want to discuss some results. These are just the beginning of the whole program. There's some basic results. In the future, I hope that I will have much more. But at least I got these basic results, which shows that the algebra should be the correct one for the A infinity. Okay, among these sub-algebras of A infinity, there are some new subalgebra. So in addition to dual algebra and also the generalization by Donnelly-Mason, there are really some new algebra. These new algebra play I believe that in the future will play a very important role, because these new algebra, in certain cases like C2 cofinite, they are also finite dimensional. So I will also discuss those modules for the vertex algebra and this new subalgebra. I call them A and V. Okay, a superscript n, not subscript n. Okay, so this is the outline. So let me first introduce this algebra. But before I introduce the algebra, I do want to give some motivation. So the motivation is the following. See, if we study Lie algebra, so universal envelope algebra is really important. See, all the kind of representation are constructed from universal envelope algebra. We have these Verma modules and so on. So this is really crucial. But why the universal envelope algebra is important? It's basically the module category for the Lie algebra and for the universal envelope algebra are actually isomorphic. So you see, you can switch between Lie algebra and the universal envelope algebra. So certainly in the beginning, you will say, okay, why can't we just use the universal envelope algebra, which was introduced first by Frank and Zhu. You can also prove that there is equivalence between module categories. Okay, but the trouble is this. The trouble is that the module for the universal envelope algebra is too weak for us. See, the universal envelope algebra, it actually must involve some infinite sums. These infinite sum does not appear for the modules we are interested in. Okay, so basically, if you want to use universal envelope algebra, you are studying much more general sort of modules, which are not really interesting for the study of like a conformal field theory. We are not interested in these modules. So okay, so the main thing that even so-called weak modules for vertex algebra do not involve such infinite sum, because the vertex operators are always low truncated. So we do not really study this kind of such a general module, and therefore, you see, we should not really use the envelope algebra. So sometimes you can use that. You can use some quotient of the universal envelope algebra to actually study, to actually construct this, for example, the dual algebra and so on. But it's not the algebra itself. And in vertex algebra, certainly we have weak modules, but weak modules are mainly, okay, if you think about this in all our work, it's mainly we use them to formulate some notions and results, but these weak modules are not what we are interested in. So in the representation theory vertex algebra, we are interested in lower bounded or gradient restricted generalized modules. So actually, the gradient restricted generalized modules are really the modules we are interested in. The lower bounded generalized modules are important. Why? Because when you prove a theorem, so the main thing that I myself have proved all these theorems for general theory, not for some particular example. When you try to prove general theory for a vertex algebra, you actually always find that in the middle of your proof or something, what you will get is a low bounded generalized module, not a gradient restricted one. And then you have to spend a lot of efforts to prove that these low bounded ones are gradient restricted. So it is actually, see, usually it's not weak module. Certainly you can also get some weak module, but we can always prove that there's some kind of a low bound. So a low bounded generalized modules are really important. And therefore, the correct category to work with is really low bounded generalized module. So that's about module. Okay, now let's look at what we already have for the associative algebra. So certainly everyone knows that we have a dual algebra. Okay, and then Donnelly-Mason generalized this to some higher level. Okay, but okay, if you had experience, you see that certainly if you only work with rational theory, means that basically it means that every lower bounded generalized module is compute reducible. So if you work with that kind of theory, then you see true algebra is indeed enough, because every module is determined by module for true algebra. But see, the one of the main problem is that we have to prove that every such lower bounded generalized module, even for rational theory, we have to prove that every lower bounded generalized module is compute reducible and so on. So this is something that you cannot use true algebra. So I think the best result is actually the given by Dong and Jiang. They actually prove that if true algebra is compute reducible, then I think a lower bounded general module is compute reducible, but they really cannot prove that irreducible lower bounded general module is gradient restricted. Okay, so that's still not settled yet. Okay, so these modules like true algebra and so on, they can be used to classify irreducible modules, but okay, the role of these algebras is really limited. I already discussed this. So one of the things is that if you are given a module for one of these associative algebra, and which is from a suitable module for the vertex of algebra, even if the even if the module is irreducible or compute reducible, the module for the associative algebra is irreducible or compute reducible, you still do not know, in general, you still do not know whether the original vertex operator module is irreducible or compute reducible. So see, I certainly means the general case. If you add some condition, that's a different story. Okay, so the goal is that we want to find an associative algebra just from a vertex of algebra, and such that a suitable category of modules for this associative algebra is see, the main thing that originally my hope is that the category of suitable category modules for this associative algebra is equivalent to the category of low bounded generalized module for the vertex of algebra. But I realized that it's not, I cannot really achieve this. So it's like almost equivalent. For that paper, I'm still writing. I haven't finished yet. It's almost equivalent. Mainly, there are the morphisms are different. So sort of like objects are basically the same, but morphism, there are something. Okay, so that's the motivation. I want to find such thing. Okay, so now I indeed achieved this. So here's the setting. Okay, the setting is that we fix gradient restricted vertex algebra. So here, the main thing that you just think that a vertex operator algebra without the conformal element. Okay, so they satisfy all the conditions except that there's no conformal element. So whatever I have will be true for vertex operator algebra. So the main thing that we are actually see the construction of this algebra is related to the kind of a module category you actually work with. So it is the lower bounded generalized V modules that we are interested. So these are so-called weak modules with compatible gradients and with also compatible operators L0 and -1. Because I'm assuming it's a gradient restricted vertex algebra, there's no conformal element. So you have to assume the existence of these operators, and then they should satisfy the usual property. Okay, so this is the setting. Okay, now the construction actually, yeah. So see, actually in the beginning when I tried to do this, I also tried to just start with just the V. Okay, because see, like Zhu algebra and the Donnelly-Mason's generalization, they all start with V and then take some quotient. But I realized that it does not work. So the main thing that we have to consider so-called column finite infinite matrices with entries in V. Okay, so I denote this space U infinity V to be the space of a column finite infinite matrices, okay, with entries in V. But see, these matrices I use the natural number, including 0, to actually to index these matrices. So elements of this space are, see, I just write, you're supposed to write infinite matrices. So I just using this kind of matrices, the VKL inside the V. The main thing that they should be column finite is that for each fixed L, you have only finitely many non-zero VKL. So that's the column finite mean. The reason why column finite is needed is that for infinite matrix, you also need a column finite to make sure that you can multiply them. Okay, so it is much easier for us to work with some particular infinite matrix. That is, I use this notation. This is notation a little bit slightly easier to be confused with the one above. But now the KL is put in the outside of the bracket. So the main thing that this matrix is just the infinite matrix with only the KL entry to be this particular element V inside of this capital V. And all the other entries are just a 0, okay? Because in general, arbitrary element can be written as an infinite sum, okay? And then you see basically we can actually define things and prove things using only this kind of element. And then all the other things are just the infinite sum. As long as these infinite sum actually makes sense, then you see it will work. Okay, so that's the reason I need to introduce this notation. Okay, so that's the last one. Just we will study this infinite V using these things. Okay. So now the main thing that we first introduce a product, okay, a product on this space. So this product, in the beginning you look at, this is very technical, but actually it's what's going on is the following. Okay, so later I will you will see more. It's that for the basically we want the this infinite matrix space acts on suitable things coming from a low bounded generalized module. Okay, how these things should act on? Basically, you just use the components of vertex operator, and then you see if you are familiar with Zhu algebra the generalization by Donnelly-Mason. So these action for these algebra are actually use only the weight 0 component of vertex operator. So these are called 0 mode. Okay, so even the Donnelly-Mason's generalization, they also use only the 0 mode. Okay, but for Donnelly-Mason, they actually apply to these acts on higher weight space, like the Zhu's algebra acts only on the lowest weight space. Okay, that's the difference. But they only use 0 mode. Okay, now for this algebra, I want to act on the module to include all the modes, all different modes. Okay, so this will actually certainly, if this can be achieved, then certainly this will give us much more power because you have all the modes. Okay, so the main thing that if you want the acting on the module to have all these modes, then you also want to come back to the U infinity V to have some product which exactly corresponding to the composition when you act on something coming out of the module, then you will have to have this definition of the product. Okay, so this product, when I write on, it's technical, but there is a conceptual way of interpret this. Okay, so I will just write on this, and in some special case, certainly it will reduce to the Zhu algebra and Lonely Mason. So the main thing that here, let's look at this. So this is the notation I use. You see the Kn and Nl are outside of the bracket. So it means that this is just a matrix with only one entry to be U and or to be V. The entry is given by these Kn and L. Okay, the product is defined using this. So here, this T is such a Laurent polynomial. Basically, this T actually also has a conceptual meaning. See, I think before when we write down such a product, we just use the binomial coefficient, but actually one can write in this way because it's more conceptual. This T is that you have this x plus 1 to this power, and then this is, I write it in this way, x plus 1, using our convention that you should expand this as negative power in x. Okay, then this t k plus l plus 1 is just the Taylor polynomial when you expand this as a power series in x inverse up to the power k plus l plus 1. That's it. Okay, so there is a meaning. That's the Taylor polynomial of the expansion of this. Okay, so that's something that which is actually, and so I say one thing I want to mention that why you have these. Okay, one can ask. These appear also in Zhu algebra. Why you have these 1 plus x and so on. These are coming from. See, when you want to like make sure that you apply to module, you have the composition corresponding to here. You want these to agree, then you have to use associativity to prove that. When you use associativity or the Jacobi identity, you will see that there will be such 1 plus x appear. So that's the reason. Okay. So certainly this is closed. Okay. So I should mention another thing is that I also use the bracket here. Okay. And then there are KL outside. So the meaning of this is that this is an element. You should view this as an element in V. And then the KL means that this is a matrix with the only non-zero entry to be what's inside at KLth entry. Okay, so that's the meaning. And so this is certainly closed. Okay, it's under this product, then the U infinity V is closed. So it is an algebra, but certainly this is not associative. So it's such a general algebra, it's not so useful. So the main thing that just to remember for Zhu algebra, what we do is that we actually want to introduce a subspace of V, and then we take a quotient. Okay, so in the beginning, I also attempt to do this. Okay, so what I'm doing is that I introduce infinity V, and given by these. So these are also similar to when Zhu introduced Zhu algebra, you just basically take some other powers. So when we define the product, we take a certain power, and then you take other powers. So it means that here the x to the power is different. So you take some other powers and so on, and also we need to actually put L minus 1, L0 and so on in. So this will take care of some important thing for so this is also needed in like a Lonely Mason's generalization. Okay. So unfortunately, okay, so in some sense that you have to take a quotient of these, but unfortunately, this infinity V does not seem to be an ideal of the algebra. So this actually I spend a lot of time. I try to prove that this is an ideal, but I think it's not, because when I calculate these things, I do not think that they belong to O infinity V anymore. So it does not seem to be an ideal. So what we can do is the following. What we can do is that we actually wanted to find a larger, certainly if you have an ideal containing O infinity V, it should be larger than this. So we want to find a larger ideal, or an ideal generated by this in a certain sense. So, but see, the main thing that our main concern is that we want to make sure that after you take the quotient, the quotient must act on something coming from the module. That is the main concern. So the strategy I'm using is that I just look at all the lower bounded generalized modules. Okay, so we now use this module to define an ideal. So that's the idea. So for module, I need to use increasing filtration. So this is yeah. So here is the idea. We want to find this Q infinity, okay, containing O infinity, such that this associative algebra will acting on something coming from the a module. Okay, so we now start with low bounded generalized module, and then we let ON. So this ON has been studied a long time ago, like for example, in Donnelly-Mason's generalization, they also use this ON. So it is just the space that you have if you have the component of vertex operator whose weight is less than n, okay, less than minus m, then when you act on these vectors, it should be equal to 0. You take all these vectors in the module, put together, these are the ON. Okay, so ON certainly has this property that ON1 is contained in ON2 for n1 less than or equal to n2, and W is a union of all these omega n. So yeah, it should be omega n. So this is increasing filtration. Okay, so this is something that we will actually have to use for all n, not just n some finite n. Okay, so what we do is that we now want to actually define an action of the U infinity V on the so-called associated graded space of the filtration. So this is the standard procedure. Given any filtration, increasing filtration, you can define the associated graded space. Okay. So then given any W in omega n, certainly we can actually write on W plus omega n minus 1, which is in the nth homogeneous space, subspace, and we use this notation to make sure to make it simpler to write. Okay, so now we actually want to define an action of this U infinity V on this GRW. So the definition is the following. We just only need to define such a linear map. It is defined in this way. Okay, so here inside this is a theta GRW. Inside I put a suitable element in this U infinity V, which is just the non-zero entry is at KL, and this WN is the abbreviation I use, and it just defined to be this. So this definition, okay, when I write this, it probably looks complicated because I have all these brackets, K and so on. But roughly speaking, it's nothing but I just see, because this residue just to take out this component which has the weight equal to L minus K. Okay, so the weight is I think it's a K minus L, and if n is not equal to L, then it's 0. But if n equal to L means that you start from the Lth sort of subspace, and then you have weight L minus K minus L operator acting on this, it will actually change the weight of this to it's actually not weight, but see, roughly speaking, it's weight, but see, it's omega n. But roughly speaking, it's like a change this space to originally it's omega L to omega K, because the weight K minus L operator will map omega L to omega K. Okay, so that's the idea. So the idea is very clear. The write down this, I need this note. Yes.
Sorry for the interruption. I think that there is a question from Fei.
Yeah, okay, maybe see, because I open my the PDF file, so I do not really see the question. So maybe you can read out.
Yeah. Fei Chi, go ahead.
Yes, I was just wondering that you're probably taking out the not the element of the weight L minus K, but you also have got the Lx to the L0 acting on V, right?
Yeah, but this will actually basically cancel the weight of V.
Oh,
that's the reason.
I see. Yeah. So this is actually for canceling.
Yeah, you basically need this. Otherwise, you do not. Otherwise, there will always be a weight V there. So that's
I see.
what we want. Okay.
I see. Thank you very much.
Okay, so now if I write on this, then it's more clear, because if the V is homogeneous, you can write this way, and this is exactly the operator of weight equal to K minus L. Okay, so I do have this here. Okay, so now see the we can actually introduce our Q infinity V and A infinity V. So here is actually there's a theorem. This theorem will allow us to introduce these things. So the theorem is that this linear map defines a U infinity V module structure on this associated graded space. Okay, so the main thing that this U infinity V now is actually a non-associative algebra. So you should just view this as a homomorphism of non-associative algebra. But the main thing is that our the endomorphism of the associated graded space is actually associative algebra. Okay, so because of this, so because then you take the U infinity V over this kernel, it should be isomorphic to a subalgebra of this associative algebra. Therefore, this must be associative algebra. Okay, so the quotient of this U infinity V by this kernel is an associative algebra, and it's certainly isomorphic to a subalgebra of this. Okay, so what we do now is that we take this Q infinity V to be the intersection of all these kernel for all the lower bounded generalized V module. Okay, so that's the Q infinity V. And then our A infinity V is just the quotient. And if I use the 1 infinity to denote the elements with all diagonal entry to be equal to the vacuum, then you see we have this theorem. Okay, so first of all, this A infinity, which is a quotient, is certainly an associative algebra, because you just if you take a quotient by one kernel, it's already associative algebra. You take more quotient, certainly it's associative algebra. And then this 1 infinity plus this Q infinity V now is the identity. Okay, so then, and also from what we actually introduced, this Q infinity V, then the associated graded space of the increasing filtration of a low bounded generalized V module is certainly an A infinity V module. Okay, so this way of definition automatically give us this A infinity V module. Okay, we do not need to spend a lot of effort to do that. Okay, but see certainly here it's easier to define the A infinity module, but see when you want to do other things, it will be difficult. So the main thing that for A infinity module, if you view this as a associative algebra, certainly it will actually have a lot of modules. But see the module coming from some V module is special, because first of all, there is an n grading, right? Because this graded space automatically has an n grading because by definition. And also there are two operators because originally we have L0 and L-1 acting on W. They induce operator are this associated graded space. So, and they satisfy certainly all these natural conditions coming from the V module. So we will call these graded A infinity module. Okay, so these modules satisfy these additional, have these additional grading, and these two operators satisfy some other conditions that's coming from the V module. So we have this special type of module for this associative algebra. Okay, so now so this is now I already finished discussion of the definition of this algebra, and automatically we obtain modules, graded modules for this associative algebra from a lower bounded generalized V module. Okay, so this is finishes the first part. Now the second part, now I want to discuss the subalgebras of this A infinity V. So the first is certainly we have to have established the connection with Joule algebra. So what is Joule algebra? Okay, so it's just this. See, we have this infinite matrices. Now what you do is that you just take all those infinite matrices with the only non-zero entry to be at 0, 0. Okay, remember we use 0, 1, 2, 3 to index the matrix. So only at 0, 0 it is non-zero, and it's equal to some element in V. So it's just given by these. Okay, so these matrices you can identify. Okay, certainly you can identify the space, this subspace of U infinity V with V, right? It's clear. And then we define this A00V is just the coset inside of this A infinity V given by these kind of elements plus this Q infinity V. So because the A infinity V is the quotient of U infinity V by this Q infinity V. So we just take these things. And then the theorem is that this A00V is closed under this operation. So that's actually very easy to see because it's just this kind of a matrix certainly is closed. And therefore it's a subalgebra. And with this particular element as the identity. And the main thing which is not easy to prove, because the reason is that Joule algebra, we have this explicit OV. Okay, you take a quotient, but now in our case, this Q infinity V is defined using all modules. Okay, so that's the reason why the proof you still take some effort. But we can prove that. Okay, basically you can prove that when you restrict to this A00V, sort of this Q infinity V intersect with this U00V, actually is this OV introduced by Joule. So therefore this is isomorphic to Joule algebra, and if the vertex operator if the V is a vertex operator, then we have a conformal conformal vector, and therefore this is in the center. Okay, this is what Joule already have, but the main thing that now we identified Joule algebra as a very, very small subalgebra in our algebra. Okay, the next one is Donnelly-Mason's algebra. So in this case, so the only difference is that in Joule algebra is you use this, the only non-zero entry is 0, 0. But now we use the only non-zero entry is still on the diagonal, but it's an n. Okay, so UNN, yeah, there should be a V is equal to this. And then again, UNNV can be identified canonically with V. Okay, so this is again, it's the case. So that's why Joule and Donnelly-Mason, they all use V to define their algebra. And then we let A, N, and V similarly to do algebra by this. Okay, the theorem is also similar. It's just this is certainly also easy to see that this is closed, because this kind of matrix is certainly, when you take the product, it's closed. And then the main important part of this theorem is that this associative algebra A, N, and V is isomorphic to the Donnelly-Mason's generalization. Okay, and if there is a conformal vector, then you have something in the center. Okay, so this is the older algebra. So there's nothing new up to now. Okay, so now the main thing that actually the interesting that we actually now can find really a lot of infinitely many new algebras. So that's the main thing. So the main thing that we actually now consider this U upper NV to be the space of all n plus 1 matrices with entry in V. And this kind of a matrix can certainly be viewed as a subspace of infinite matrices. Okay, so we view this as a subspace. And then the 1n is the elements of this finite matrices with diagonal entry to be equal to 1 and all the other to be 0. Then we just let A and V basically just to be the corresponding subspace in the A infinity V. Okay, so then we can prove the following theorem. This is easy, that this is indeed also closed under this operation. So the main thing that you consider the subspace of finite matrices, then certainly it's closed. Okay, and the identity is this. So this is sort of straightforward. And the main thing that we also want to consider A and V modules. So these are new associative algebras. Okay, so we can also construct modules, because for A infinity V, the graded associated graded space of a module is so yeah, here I forgot to write that W is a lower bounded generalized module, and then we can let just GRNVW to be just only the sum from the direct sum from 0 to n. Okay, the associated graded space is supposed to be sum from 0 to infinity, but now we only take the up to this capital N. Okay, so this is a subspace of the associated graded. Then okay, this is almost a trivial, because you can just obtain from the associated graded space. This GRNW is an ANW module, so we do have such a module. So again, this module has some additional property that there is a grading, because given by this, and then additional operator also. So these are also called a graded A and W module. Now the other theorem is also interesting, is the following, that we all know that for Drew algebra and Donnelly-Mason's generalization, if the vertex of algebra is C2 cofinite, then these algebras are finite dimensional. Okay. Now, for A infinity, it cannot be finite dimensional, because the graded associated graded space is always infinite dimensional if the original module is infinite dimensional. But these A and V, they are actually finite dimensional if the V is like a C2 cofinite and satisfy this CFT type. I myself prefer to call this positive energy, but people usually call this CFT type. So these are also finite dimensional. So that's the nice thing, if the condition is satisfied. So that's also something nice. Okay. So now let me discuss the results. So the sort of initial results I have obtained. Okay. So the first I want to discuss low bounded generalized V modules and graded A infinity modules. What are these connections? Okay, so I actually obtained the mainly. So there there are some small results, but these are the main theorem. So mainly, I want to discuss irreducible and compute-reducible low bounded generalized V modules. So the nice thing now is that a low bounded generalized V module W is irreducible or compute-reducible if and only if the corresponding graded A infinity V module G W is irreducible or compute-reducible, respectively. So this is a very nice. This means that see, basically this kind of a result is what we want, because basically for like a Drew algebra or Donnelly-Mason generalization, they cannot really have this kind of result. Here I do not have any condition. Okay, so just to look at this, there's no condition at all. That is the associated graded space, whether it's irreducible or compute-reducible, determine whether the original low bounded generalized V module W is irreducible or compute-reducible. Okay, certainly I shall say that this is this kind of a result shows that A infinity V module is the correct the A infinity V is the correct algebra, but see, certainly this is not like a easy for calculation, because A infinity V is something not easy to calculate. But see, this is just like a universal envelope algebra. It provides a framework for future study. That's the main thing. Okay. Now, certainly, see the another results is that if you want to have, this is certainly even for Drew algebra, you will also get this. That's the equivalence class of irreducible modules is in bijection with the equivalence class of irreducible graded infinite modules. This result is certainly needed here, because any kind of reasonable algebra must give this kind of result. But this, if you want this kind of result, that's the best to look at just Drew algebra, because it's much simpler. Drew algebra also have this bijection. Okay. So so this is the results I obtained for the A infinity V. Then see the actually see the A infinity V is too big. Okay, but see, I really need to write a lot more papers. Like for example, A infinity V, my guess, I haven't write this down yet. My guess, like for alpha and Lie algebra vertex operator generated by given by the generalized Verma module for alpha and Lie algebra, my guess is that A infinity V for that kind of vertex operator algebra should be just the universal envelope algebra for the alpha and Lie algebra. So that's my guess, or some minor modification. But see, roughly speaking, it should be this. Okay, so this kind of algebra, A infinity V, is still too large. Okay, it is too large. It is infinite dimensional and so on. Okay, so now we want to look at ANV module, because ANV module in many cases, like certainly in the C2 cofinite case, but see, it is also possible in other cases, it will be finite dimensional. And even if it is not finite dimensional, when n is small, it is possible to do calculations in the future. At this moment, I do not really know how to do this yet, but see, I hope we can do this, because like the Drew algebra is just Drew algebra is actually isomorphic to this A upper 0 V module. Okay, so this is a special case. I hope that in the future we can do calculations. So I want to discuss the connection between this kind of algebra, which is relatively easy to handle, with these kind of low bounded generalized W. Sorry, here I have a typo in the title. It should be V module. Okay. So the first two results is that I do not have any additional assumption. Okay. So if we want to get better results, we have to. Now the assumption is very weak, because we even do not have a conformal element. We even do not have. It's just a gradient restricted vertex algebra. So in this case, okay, what I can obtain is that if you have a lower bounded generalized the V module W, which is irreducible or compute-reducible, then see, remember we have this subspace of the associated graded space. So we take this subspace, which is AN, it's an ANV module, a upper N V module. So this is I already discussed. So if W is irreducible or compute-reducible, then this ANV module is also irreducible and compute-reducible, respectively. So this direction does not need any additional conditions. So that's easier because in some sense that this is certainly certainly should be true because W is irreducible and compute-reducible usually is always stronger. Okay. Now the other thing that actually in this case we can also derive that the set of equivalence class is actually in bijection. Certainly, for Druce algebra this is a special case. That's the case of n equal to 0. That's Druce algebra case. Okay, so this is this theorem which we do not need any additional condition. Okay. Now we need some additional condition is mainly we need only L plus 1. See, when we introduce gradient restricted vertex algebra, we only have L minus 1 and L 0. There's no L plus 1. So one of the thing about the gradient restricted vertex without L plus 1 is that the grading the grading is mainly for the module. Okay, mainly for the module. For the module, the grading you can shift. You can shift the grading by any number. You will still get a module for the gradient restricted vertex algebra. But okay, if we add L plus 1, then module for this kind of vertex algebra called the Möbius vertex algebra, you cannot shift the grading of the module. So that's something we need. Okay, so this is the reason why we need this condition. So this is a very minor condition. It does not really give you any kind of serious restriction. So the main thing that we need this kind of vertex algebra. So V is such a Möbius vertex algebra. But see, there is additional assumption. Okay, the additional assumption that you have to make sure that, so in the future, I hope to improve these things, but at this moment, this is what I have, is that you just look at the differences of the real parts of the lowest weights of the irreducible lower bounded generalized V modules. Okay, if these differences are less than or equal to some n, capital N, okay, then we have the following conclusion. A lower bounded generalized V module of a finite length, certainly it should be finite length, because if it's infinite length, then so the main thing that finite length is irreducible or completely reducible if and only if this graded ANV module is irreducible or completely reducible. So the only sort of direction is that if this ANV module is irreducible or completely reducible, it implies any of these finite length generalized low bounded generalized V module is irreducible or completely reducible. So that's the only direction, because the other direction it's already proved in a more general case. Okay, so in this case we can prove this. So here the main thing that the main assumption is that the differences between these lowest weights of irreducible low bounded generalized V module should be less than or equal to n. So this is something that which is not always easy to verify, but in some particular situation, if you already classified irreducible modules, then see you can still do that. Okay. So the now the last result, okay, the last result I want to discuss is the following: is that see as I said, for in the representation of vertex algebra, the truly interesting module are actually gradient restricted. So because the low bounded, because the infinite dimensional homogeneous space is still not does not perform well, like under contra gradient and so on. So we are interested in gradient restricted modules, and then one of the important things you want to see whether a low bounded generalized module is actually a gradient restricted. So this is one of the important type of problem. So here is a result. I need some stronger condition, and then one can prove that lower bounded generalized V module can be under what kind of a condition it can be written as direct sums of irreducible ordinary V module. So basically, if you have an irreducible gradient restricted generalized module, it must be ordinary module. So we only need to discuss this case. Okay, so now the theorem is the following. V should be still a Möbius vertex algebra. And here we assume that all those ANV are finite dimensional. Okay, so for all n, yeah, okay, here I think I have made a typo, is that this should be AN prime V should be A upper n prime V. A lower is the notation used by Darnley Mason. So that's a different algebra. So here I have to use upper n prime. If all these are finite dimensional, okay. So the certainly in the C2 cofinite case, this is true. Okay, so we do know that there are a lot of vertex operators do satisfy this condition. And then the main thing that if these algebras are finite dimensional, then we must have only finitely many irreducible ordinary V module. We must have a finitely many irreducible, because the equivalence between the bijection between irreducible modules. So we just take these finitely many irreducible modules, and then you just take n such that differences between these are actually smaller than n. Okay, then a low bounded generalized V module of finite length. Okay, or you just have a gradient restricted generalized V module without the finite length condition. These things are actually equivalent. I think I proved it in one of my paper. Then these things must be a direct sum of irreducible ordinary V modules. Okay, but if and only if the graded AN V module GRNW is completely reducible. Okay, so that's the last result I want to actually report here. So yeah, so basically this is the main thing I want to discuss. I still have a lot of things I want to work out, but see, I think that the main thing is that the first thing that we wanted to establish suitable categorical sort of almost equivalence and so on. And then we want to prove more theorem like the complete reducibility, irreducibility, and also whether an irreducible low bounded general module is gradient restricted. Okay, so this is an unsolved problem, because if this problem can be proved, this kind of things can be proved, then see we actually can say that if the dual algebra is is simple, then every low bounded general module is completely reducible. Okay, so I think I stop here.
Great. Let's thank our speaker.
Okay, thank you.
Thank you so much. Are there any questions for our speaker? Feel free to unmute yourself and go for it if you have a question.
Yes, regarding the almost equivalent you have mentioned. So what's the difference? What actually makes the difference?
Yeah, it's mainly see the main thing that from W to its graded associated graded space. This is not a nice equivalence of category. So you have to sort of one actually have to I think the enlarge the category by putting more morphisms together with the associated graded space. Then you will be able to prove some kind of equivalence. So that is the main subtlety. Okay, but see, for these results I discussed here, these are all about objects. So basically, objects are, roughly speaking, they are equivalents. The main complication is the morphism.
Thank you.
Okay, thank you.
Any more questions? And I'll stop the recording now. I'm sorry that I forgot before.